This is the fourth video in a series devoted to differential equations. And let's see where we are so far in this course. So far we can solve first order linear differential equations and separable differential equations. And we've also explored methods of turning nonlinear, non-separable differential equations into separable differential equations. But we've only looked at that for a couple of very special cases. And in today's video, we're going to look at it for a couple of other special cases, as well as prove a result as to when it might be possible to make this transformation of first order nonlinear non-separable into a separable differential equation. So the first class of examples we'll look at are so-called Bernoulli equations. And a Bernoulli equation is a differential equation of the following form. We have y prime plus a of x times y equals b of x times y to the r, where r is not 0 and it's also not 1. You might say, well, why do we exclude 0 and 1? And that's because if r was equal to 0 or 1, this would be a linear differential equation. In fact, I think for r equals 1, this would be a separable differential equation even. But we know how to solve those types of differential equations by previous work, so this doesn't really gain any new information. Okay, so we're going to build a general solution strategy for solving these Bernoulli differential equations first. So I've copied my differential equation up here. Like I said, we have y prime plus a of x times y equals b of x times y to the r. Again, I'd like to underscore that r is any real number that is not equal to 0 or 1. Okay, now we're going to do something which will become a little bit more standard as we move on with the course, and that is solve the associated homogeneous differential equation. So let's recall that the associated homogeneous differential equation is y prime plus a of x times y equals 0. Okay, great. But how could we solve that? Well, it's pretty easy to solve this. Notice that this is indeed separable. We can write this as y prime equals negative a of x times y, and then rewrite this as dy over y equals negative a of x dx, and then take the antiderivative of both sides. In fact, taking the antiderivative and then solving for y, which I'll skip because it's covered in previous videos, gives us the following equation for the solution to this associated homogeneous equation. So we have y naught, I'll call that the solution, is equal to e to the minus antiderivative of a of x dx. So that should look kind of familiar to something we did before when we were solving first order linear differential equations, but it's playing a different role here. Okay, so now let's notice that since y naught is a solution to this equation, that means that y naught prime plus a of x times y naught is equal to 0. And that's really a defining property of this function, and we're going to use that with our calculation. Okay, so now let's make a substitution. So we'll substitute y equals y naught times, I'll call it z. Okay, good. But now let's take the derivative here and notice that y prime is equal to y naught prime times z plus y times z prime using the product rule. And now let's insert this substitution for y into our original differential equation. Not the homogeneous one, but our original differential equation. So let's see, the y prime term can be written like this. We have y naught times z, let's see, y naught prime times z plus y naught times z prime, so that's y prime. And then we have plus a of x times y naught times z. And then we have this is equal to b of x times y naught to the r times z to the r. But now let's notice that we could factor a z out of this stuff that I'm underlining in purple. So we could factor a z out of this, and we have exactly this equation over here. So that means that this z underlined stuff indeed cancels out to 0. And it cancels out to 0 because of how we chose y naught to be a solution to this associated differential equation. So let's see, that gives us y naught times z prime equals b of x times y naught to the r times z to the r. But we could maybe divide both sides by y naught, and that's going to turn this to y to the r minus 1. And we can do that on an interval where y naught is not equal to 0. And so we'll just have to keep that in mind. This is not always available, but it's really best to look over those things when we're working through examples. But what are we left with? Well, luckily we're left with a separable differential equation. So let's note that this is indeed separable. And we could solve this separable differential equation for z. Of course, exactly what solution we will get will depend on this value of y naught right here, as well as this value of r. If you would want to write maybe the next to last step, it would look something like this. We have dz over z to the r equals b of x times y naught of x to the r minus 1 dx. And I put a y naught of x there because recall that y naught is not a variable. It's a function of x, which we've previously determined. That's what makes this thing separable. And then you would take the antiderivative of both sides, and then you would achieve a formula for z. But we can use that formula for z and plug it into this, and we've got an equation for y, and we have solved our differential equation. So like I said, that's our solution strategy. I guess if you're really interested, you could write down z in terms of r and some like crazy antiderivative, but I don't really think it's worth it. I think maybe the best idea is just to think about this as like a flow chart. Solve the associated homogeneous differential equation, make this substitution, solve the remaining separable differential equation. Okay, let's look at some examples. So our first example will be y prime minus y equals x times y squared. So that's most definitely in the form of this Bernoulli differential equation. So our first step will be to solve that associated homogeneous differential equation. That's y prime minus y equals 0. In other words, we have y prime equals y. So we could solve that with separation of variables. Notice we would get something like dy over y equals dx, but we can really just think through a catalog of functions here, and then which function will produce itself when taking the derivative, and that function is any constant multiple of e to the x. So we could write y naught, because that's written for the solution to this differential equation, is a constant times e to the x, but I'm just going to write it as e to the x because in our substitution we can, you guessed it, absorb the constant into our variable z. Okay, so that's our next thing. So the second step will be to set y equal to y naught times z. In other words, e to the x times z. But now taking the derivative here, we see that y prime is equal to z prime times e to the x plus z times e to the x. That's because the derivative of e to the x is e to the x using the product rule. And now we'll take this substitution that we've made for y and plug it into our original differential equation. And that's going to give us our new differential equation, which magically is separable from what we saw on the last board. But let's write it all out. So we'll write y prime as z prime e to the x plus z times e to the x, and then minus y. But y is equal to z times e to the x by our substitution. And then this is going to be equal to x times y squared, but that'll be z squared e to the 2x. That's because e to the x quantity squared is e to the 2x. Now let's notice some things cancel. So this guy will cancel this guy. And then from there, we can maybe multiply both sides of this by e to the minus x to cancel it out even more. That's going to cancel this e to the x and this e to the 2x down a little bit. And that'll leave us with something like this. We have z prime equals x times z squared times e to the x. And now from there, we can do our separation of variables. That's going to give us dz over z squared equals x times e to the x dx. And then take the antiderivative of both sides. So the antiderivative of 1 over z squared will be minus 1 over z. And then the antiderivative of x e to the x, that actually requires integration by parts. I'll let you guys work that out. We did some review of problems like that earlier, but what you end up with is x e to the x minus e to the x, and then plus our constant of integration. Okay, so there we've got our value for 1 over z. We can negate and take the reciprocal to give us z equals negative 1 over x e to the x minus e to the x plus c. And then let's bring that up here, and then we can finish this thing off by calculating y via this substitution. So on the last board, we determined that our function z was negative 1 over x times e to the x minus e to the x plus c. But let's recall that that's not a solution to our differential equation. A solution to our differential equation is our function y naught, which we determined to be e to the x times this function z. And so that's what we'll use to finish this thing off. We have y equals e to the x times z. But since we've got a numerator and a denominator here, and furthermore, I've got e to the x's in the denominator, it actually makes sense to rewrite this as z over e to the minus x. But that's exactly the same kind of thing. So that means we have z is negative 1 over e to the minus x times x e to the x minus 1 minus e to the x plus a constant. Now we can distribute this e to the minus x inside, and we'll have y is negative 1 over x minus 1 plus a constant times e to the minus x. And that would be our final solution for this Bernoulli differential equation. Okay, let's do another example. So here's our second example. We have y prime plus y over x equals x cubed times y cubed. So let's start, like we did before, by solving the associated homogeneous differential equation. We have y prime plus y over x equals 0. Okay, but notice that this is most definitely separable. We have y prime equals negative y over x, which we can rewrite that kind of sketchily as dy over y equals negative dx over x. Again, splitting up the y prime as dy over dx. And like I said, this is most definitely sketchy notation, but it works out, so it's like kind of okay. And we discussed why it works out in the previous video. Now we take the antiderivative of both sides, and that's going to leave us with something like the natural log of the absolute value of y equals minus the natural log of the absolute value of x, and then plus some constant. And then from here, we're going to make a simplifying assumption, and that is that any initial condition we would be given, y of x naught equals y naught, gives us a positive value of y where x is also positive. And that allows us to assume that these values of y and x are positive, so we can get rid of the absolute values. That's going to simplify our lives quite a bit. So we have the natural log of y equals the natural log of 1 over x plus some constant, where I took this minus sign in and then just took the reciprocal. Now we can exponentiate both sides, and that's going to leave us with y is equal to e to the natural log of 1 over x plus a constant, but that's the same thing as e to that constant times e to the natural log of 1 over x, but that'll just be 1 over x. And another simplification that we'll make, and this is allowed because we're not really trying to solve this associated differential equation. We want to solve our original differential equation, which will involve multiplying the solution of this by some other function, that means that we can kind of get rid of this constant right here and just absorb that constant into the multiplication of with our other function, which we'll call z later. Great. And now we can exponentiate both sides, and we'll immediately see that y is equal to 1 over x, and let's call that y naught. Okay. And then let's recall that from that, we would set y equal to z times y naught. So that would be z over x. And then we substitute that into our given differential equation. So let's do that. Okay, so now substituting y equals z over x into our differential equation, keeping in mind that z is a function of x, will give us something like this. So y prime will split into two terms. We'll have z prime over x minus z over x squared. That's using the product rule, thinking about this as z times x to the minus 1, if you will. Okay, and then we have this is added to y over x, but notice y over x will be z over x squared by our substitution rule, and then this will be equal to x cubed times y cubed, but that'll give us z cubed over x cubed. So we get quite a bit of simplification now, which is pretty nice. Notice that this will cancel with this, and then this x cubed here will cancel with this x cubed here, leaving us with something like z prime over x equals z cubed. And that's pretty nice. But again, it's a separable differential equation, which means we can solve it fairly easily. Moving things around, we see that dz over z cubed equals x dx. Then we can antiderivative both sides. That's going to leave us with something like minus 1 over 2 times z squared equals x squared over 2 plus a constant. Okay. And then from here, I can multiply both sides by 2 to get rid of that 2 in the denominator. That'll leave me with minus 1 over z squared equals x squared plus a constant. I get that by absorbing the 2 into the constant. Then I can take the negative reciprocal of both sides. That leaves me with z squared equals 1 over c minus x squared, where again, you guessed it, I absorbed the minus sign into the constant. And then finally, I'll have z equals 1 over the square root of c minus x squared, where I took the positive square root because of our assumption before that our initial condition gave us positive values. If it had given us negative values, then we would have had the negative square root. But of course, all of that would have shaken up at this stage right here where we would introduce the initial condition. Okay, so let's see what we get from here. So recall that y is equal to z over x, which means our final solution will just be this times 1 over x. You could write that a number of different ways, maybe as 1 over the square root of c times x squared minus x to the 4th is kind of a nice way to write it, where we take that x in the denominator, pull it into the radical by squaring it. Okay, so now that we've done a couple of examples of solving these Bernoulli differential equations, I want to look at kind of a big question of what is a sufficient condition for the ability to follow this diagram. In other words, to transform a first order nonlinear non-separable differential equation into a separable differential equation. So like I said before, now we're going to look at the following kind of big question. And that is, given an arbitrary first order differential equation, which is of course of the form y prime equals an arbitrary function of x and y, what is a sufficient condition for the ability to make a translation into a separable differential equation? And although we will find this sufficient condition, it's not a necessary condition. And furthermore, it's not really going to help us a ton because it's a little bit technical. This is maybe just kind of an exploration. And so in terms of our setup, that is really, when is this diagram possible, this transformation diagram? Okay, so let's start with our arbitrary first order differential equation, and then let's make a substitution. So let's substitute y equals u times y1 and just see what this starts to look like. So if y is equal to u times y1, then that means y prime is equal to u prime times y1 plus u times y1 prime, which means our original differential equation looks like u prime times y1 plus u times y1 prime equals f evaluated at x, u times y1. So we've done all of those substitutions. And so we've spread out the left-hand side of this equation. And now we'd like to make some wishful thinking that perhaps our substitution makes the right-hand side of the equation transform in a way so that we can gobble up part of the left-hand side of the equation. So I'll put an equality here and say that this equality is really wishful thinking, which is in fact a really important technique in math, the technique of wishful thinking, but this will end up being our condition, our sufficient condition for translation into a separable differential equation. So our wishful thinking is that we can choose y1 so that this thing over here turns into a function of u times y1 prime. So let's put that in here. So our wishful thinking is, can we choose y1? Remember, y1 is a function of x that makes this occur right here. Okay, so if we can, what does our differential equation look like? Well, it looks like this. We have u prime times y1, and then we'll move the u times y1 prime over, and that'll look like g of u times y1 prime minus u times y1 prime. And then from here, perhaps we could divide a y1 prime out. That'll give us g of u minus u times y1 prime. And then now we have a separable differential equation. It may not quite look like a separable differential equation, but let's recall that we've chosen y to be just some function of x, just like we did before. One time it was 1 over x, one time it was e to the x, maybe it's some crazy function of x. But needless to say, what we can do is take this u prime and write it as du by dx. And then we have du over g of u minus u on the left-hand side of the equation. And then on the right-hand side of the equation, we have y1 prime over y1. And those are both functions of x. So let's put y1 prime of x, y1 of x, and then a dx. But now we can just take the antiderivative of both sides, and we've got some implicit description of our function of u in terms of x. Okay, so I guess maybe we should drill down on what made this possible. And the thing that made this possible is answering this question. Can we choose some function y1, I'll say y1 of x, such that f evaluated at x, u times y1 of x, in fact simplifies to a function just of u times the derivative of y1. And so this quite technical condition is exactly what this sufficient condition is for the ability to make this translation. Okay, so like I said, this is quite technical, and in general, this is not actually super helpful. But if we restrict this to some so-called homogeneous differential equations, which we will define, we'll see that this actually allows us to solve a new class of differential equations. So we just came up with a pretty technical condition for the ability to make this translation. Now we're going to look at a special case. And that special case is our given differential equation is actually a homogeneous differential equation. And we've been kind of fast and loose with the definition of a homogeneous differential equation. But the proper way to write it down is it's a differential equation of the form y prime equals f of xy, where f of xy is in fact really just a function of one variable, and that single variable is y over x. Okay, so like I said, that is a definition for a homogeneous differential equation. And in fact, we can always make a change of variables for this class of differential equation to translate. And what's that change of variables? Well, we'll substitute the following. Let's say y is equal to x times u. And that substitution is fairly intuitive because it simplifies what's going on within this function h. Okay, so now our original differential equation, which is up here, I'll star it in red and bring that down, looks like this. We have y prime, which will turn into x times u prime plus u using the product rule equals h evaluated at u. Again, that's from our substitution, but this is most definitely separable. And we can see that it's separable by working out a couple of details. This is the same thing as x du dx equals h of u minus u, which we could maybe write this as du over h of u minus u equals dx over x. And now it's like classically separable. Okay, so just to reiterate, if we have a homogeneous differential equation, then we can always translate into a separable differential equation via the following substitution. So let's look at a couple of examples. So our first example will be y prime equals y plus x times e to the y over x. So let's first check that this is homogeneous. And we'll do that by splitting this fraction up. So that'll give us y over x plus x over x, which is 1, times e to the y over x. So that's definitely homogeneous because y and x only appear as a grouping, which is this quotient. Okay. So now let's make our substitution, and our substitution will be y equals u times x, and that's going to turn the left-hand side of this into x times u prime plus u, and it'll turn the right-hand side into u plus e to the u. Okay. Then where can we go from here? Well, we can use separation of variables technique. So we'll start by noticing that this u will cancel with this u, and then we can write this u prime as du by dx, allowing us to sketchily write du over e to the u, which is the same thing as e to the minus u, equals, let's see, dx over x after we move everything around. And then we'll take the antiderivative of both sides. So that's going to give us minus e to the minus u from this left-hand side equals the natural log of the absolute value of x plus some constant. And now we'll negate both sides. That'll give us e to the minus u equals that constant minus the natural log of the absolute value of x, where I've absorbed that minus sign into the constant. Now I can take the log of both sides. That'll leave me with minus u equals the natural log of c minus the natural log of the absolute value of x. And then finally we can negate to bring a minus sign over here. And we have u equals minus the natural log of that stuff. Then finally, since u is not our final solution, but just a portion of our final solution, we'll multiply by x, and that will give us our final solution. So y equals negative x times the natural log of that constant minus the natural log of the absolute value of x, and that would be our final solution to this example. Okay, let's do another. So for our last example, we'll have an initial value problem. So the starting differential equation is x squared times y prime equals y squared plus xy minus x squared. And then our initial condition is y evaluated at 1 is 2. So the first thing to do is to check that this is indeed a homogeneous differential equation. And in order to do that, we want to make sure that if we solve for y prime, what we're left with is just a function of y over x. And in fact, it is, because we can write this as y prime equals y over x quantity squared plus what we get when we divide by x squared. That'll be y over x and then minus 1. That's most definitely a function of y over x. Okay, then next we'll make our substitution. Y is equal to x times u, and see what that does to our differential equation. So that's going to give us x times u prime plus u from the product rule on the left-hand side. And then on the right-hand side, we'll have u squared plus u minus 1. Okay, then we see that this u right here will cancel with this u right here, leaving us with x times u prime equals u squared minus 1. And now from there, we can use separation of variables technique. That'll give us du over u squared minus 1 equals dx over x. And then from here, we'll probably want to do a partial fraction decomposition on this term. I won't work out the details, as that's generally a prerequisite for a course like this, and we did this pretty much exact problem on a previous video. But needless to say, this breaks up into 1/2, and then we have 1 over u minus 1 minus 1 over u plus 1. So like I said, you can check that, but that's pretty easy to see. If we were to give ourselves a common denominator, we would have a u plus 1 here. We would have a u minus 1 here. Doing that subtraction, we would give us a 2 in the numerator. That cancels out with this 1/2. Okay, so now we can bring that over here and start to finish this thing off. So that means we have 1/2, and then the antiderivative of 1 over u minus 1 minus 1 over u plus 1 du is equal to this antiderivative of x dx. So the antiderivative of x dx will give us the natural log of x plus some constant. You might say I need the absolute value of x, but notice our interval of validity is only positive real numbers, so I don't need the absolute value here. I know that because I've got a discontinuity in this original differential equation, which splits up our possible intervals of validity to negative real numbers and positive real numbers, but then my initial condition means that I indeed only need positive real numbers. Okay, so anyway, now we can take the antiderivative here. That'll leave us with 1/2. We have the natural log of u minus 1 minus the natural log of u plus 1 equals the natural log of x plus some constant. And then we can, in fact, use our substitution right here to figure out the value of that constant at this stage. I think that's maybe kind of a nice trick to keep it simple. So notice if y equals x times u, that means u equals y over x. But that means u evaluated at 1 will be the same thing as y evaluated at 1, which is 2, because it's 2 over 1. So now plugging that into our differential equation will give us 1/2. The natural log of 1 is 0, and so we'll have minus the natural log of 3. So we've got 1/2 times the natural log of 3. And then this equals the natural log of, well, that's going to be x equals 1, so the natural log of 1 is 0. So this equals our constant c. But now we can bring this -1/2 inside of the natural log, giving us the natural log of 1 over the square root of 3 equals our constant c, which means that e to the c will in fact be 1 over the square root of 3. And that's actually important because e to the c is how this thing will show up when we get to it. Okay, so let's maybe summarize what we have on the next board, and then we'll finish it off. So using the substitution y equals xu, we got the following equation involving u and x, where I've put my constant in there. And also from the last board to this board, I used a logarithm rule to combine these two things. Okay, so now from here, I'm going to simplify it a little bit more. So I'll multiply both sides by 1/2. So multiplying both sides by 1/2 will give me a 2 here, and it'll also give me a 2 here. And then let's also use logarithm rules to simplify that right-hand side. So this will be the natural log of x squared plus the natural log of 1 over 3. That's because I bring that 2 inside the natural log and it squares things. Okay, but then if I have a sum of natural logs, that's the same thing as a natural log of products. That gives me the natural log of x squared over 3. Great. But now look, I've got a pure natural log on the left-hand side and a pure natural log on the right-hand side. That's a good place to be because that means I can exponentiate both sides, giving me u minus 1 over u plus 1 equals x squared over 3. So something like that. And now let's go ahead and solve for u. So we can do that by cross multiplying. That'll give us 3u minus 3 equals x squared times u plus x squared. We can collect all the u's on one side and everything without a u on the other side of the equation. That leaves us with 3u minus x squared u equals x squared plus 3. So I took this 3, I moved it over here, and I took this x squared u and I moved it over there. Now I can factor a u out of the left-hand side. That leaves me with u times 3 minus x squared equals 3 plus x squared, where I just like swap that to make it look a little bit more symmetric. I kind of like that. But then finally, we can have u equals 3 plus x squared over 3 minus x squared. But then recall that our final answer is not u, it is y, which is x times u. So that gives me my final solution. Y is 3x plus x cubed over 3 minus x squared. And now we can really hone in on the interval of validity. And that is because the interval of validity will be a place where this thing is continuous that includes the initial value or the initial x value plugged in, and that would be 1. And so notice our interval of validity here will be 0 up to the square root of 3. So you might say, well, why isn't it minus square root of 3 up to square root of 3? Because that's where this guy is continuous. That's because our original differential equation after dividing by the x contains functions that are not continuous at 0, so you have to restrict for 2 reasons. Okay, so this would be our final solution to this differential equation. So I'll leave you guys with some warm-up exercises. So let's recall the 2 main things we discussed today were how to solve Bernoulli differential equations, as well as how to take first-order homogeneous differential equations and translate them into separable differential equations and then solve. And so these warm-up exercises represent some of each of these. So let's see what we have. We have 7xy prime minus 2y equals minus x squared over y to the 6. We have xy cubed times y prime equals y to the 4th plus x to the 4th. Next up is x squared times y prime plus 2xy minus y cubed. We've got an initial condition of y of 1 equals 1 over root 2. And then finally, y prime equals xy plus y squared over x squared, an initial condition of y evaluated at -1 equals 2. And that's a good place to stop.